Welcome to Spaceverse, your portal to cosmic adventures. If the heart of our galaxy were throwing a party, the DJ would be a supermassive black hole. And trust us, it's putting on quite the show. Thanks to NASA's James Webb Space Telescope, astronomers have just captured the longest and most detailed view yet of the cosmic chaos at the center of the Milky Way. That's right, we're talking about Sagittarius A, the supermassive black hole lurking some 26,000 light-years from Earth. But this isn't just a dark, silent void. Far from it. Surrounding the black hole is a swirling accretion disk, a cosmic maelstrom of gas, dust, and magnetic fields, all spiraling at incredible speeds. And now, for the first time, we're seeing it in stunning detail. Flaring, flickering, and glowing in a mesmerizing dance of energy. With Webb's powerful infrared vision, scientists observed Sagittarius A erupting in bursts of light, some short and dim, others long-lasting and brilliant. These flares appear and vanish with no apparent pattern. One moment, the center flares up like a celestial flashbulb. And the next, it slips back into quiet darkness. It's as if the black hole is pulsing with energy, but to a rhythm we still don't fully understand. The lead researcher, Farhad Yousefzadeh from Northwestern University, describes it as constantly changing, bubbling brightness. Imagine a galactic lava lamp, only the stakes are billions of times bigger, and the physics behind it may hold the key to understanding the universe's most extreme environments. Over several months of continuous observation, Webb recorded subtle changes, shifts in brightness, the timing of flares, and the intensity of light across different wavelengths. These clues may finally help scientists decode how black holes feed, what kind of material they're consuming, and how those feasts shape the galaxies around them. And why is this important? Because studying Sagittarius A isn't just about peering into the middle of our Milky Way, it's about unlocking the secrets of black holes everywhere. These mysterious giants influence star formation, galactic evolution, and even the flow of time and space itself. This new research, published in the Astrophysical Journal Letters, marks a major milestone in black hole studies. And with every observation, Webb continues to redefine what's possible in the world of infrared astronomy. So next time you look up at the night sky, remember that at the center of it all, something wild, unpredictable, and beautifully complex is unfolding. And we're only just beginning to understand the rhythm of the universe's most mysterious dance floor. At the very heart of our Milky Way galaxy, hidden behind clouds of dust and light-years of cosmic distance, lies a monster cloaked in mystery. Sagittarius A, the supermassive black hole, 4 million times the mass of our Sun, a gravitational titan so dense, not even light can escape its pull. But what if we could peer closer, beyond the dark veil? This artist's illustration offers a glimpse into the unimaginable, a swirling maelstrom of gas and energy, the accretion disk, orbiting the black hole like water spiraling down a cosmic drain. The intense gravity bends light around the black hole, making the glowing disk appear to wrap around it entirely. It's an illusion sculpted by physics itself. But this isn't just a quiet, eternal swirl. It's alive with energy. Massive flares, some as intense as solar flares, but far more powerful, burst from the disk. These eruptions mark brief, violent moments of matter colliding, compressing, and releasing enormous amounts of energy near the black hole's event horizon. Thanks to the James Webb Space Telescope and its ultra-sensitive near-infrared camera or NIRCam, we're not just imagining these events, we're observing them in real time. Led by astronomer Farhad Yousefzadeh and a global team of researchers, Webb's campaign to watch Sagittarius spanned 48 hours over the course of a year, with each observation lasting up to 10 hours. And what they found was breathtaking. Flares erupted 5 to 6 times a day. Smaller flickers and bursts danced in between. It was a dazzling, chaotic display, a galactic fireworks show taking place at the edge of darkness. But what causes this violent brilliance? That's the mystery. Yousefzadeh proposes that two separate forces are at work, one behind the small, rapid flickers, and another behind the massive, long-lived flares. The smaller flickers? They may stem from subtle, internal disturbances in the accretion disk, perhaps compressed pockets of hot plasma jostling around due to turbulence. The result, brief, sharp flashes of radiation. Incredibly, this resembles something much closer to home: solar flares from our own sun. Magnetic fields twisting, building, and snapping, releasing pent-up energy in violent bursts. Only this time, it's happening in one of the most extreme environments in the known universe, where space-time itself is warped and light struggles to break free. This is exo-astrophysics at its most thrilling, comparing the behavior of our own sun to the chaos swirling around a supermassive black hole. And as more data pours in from the Webb telescope, each flicker and flare adds a piece to the puzzle of how black holes interact with the universe around them. From chaos comes clarity. From darkness, discovery. Because in the cosmic ballet of matter and gravity, Sagittarius A is the lead dancer, and thanks to Webb, we finally have front row seats. Deep in the heart of our galaxy, 26,000 light-years away, lies a sleeping monster, the supermassive black hole known as Sagittarius A. For most of its time, it remains quiet, invisible, motionless. But every so often, it erupts, unleashing a flare of energy so powerful, it lights up space like a galactic heartbeat. These brilliant flares, according to astrophysicist Sgr A and his team, are no ordinary bursts of light. They're triggered by rare and explosive events called magnetic reconnections. Picture two massive magnetic fields colliding, twisting, snapping, and reconnecting, and in the process, accelerating charged particles to near the speed of light. What follows is a blinding flash of radiation released in mere seconds. A cosmic spark that pierces the silence. In a sense, JWST explained, it's also an electric reconnection, a phenomenon not unlike the static electricity that shocks your finger on a doorknob, but magnified on an interstellar scale. And thanks to the James Webb Space Telescope, scientists are now able to witness these flares in stunning new detail. Using Webb's powerful near-infrared camera, or NIRCam, JWST's team monitored Sagittarius A simultaneously in two different wavelengths, 2.1 and 4.8 microns. This dual-perspective approach allowed them to track subtle changes in brightness in real time. What they found? Something no one had ever seen before. For the first time, a slight delay was recorded between the flares and the two wavelengths. The shorter wavelength, 2.1 microns, flared up first. The longer wavelength, 4.8 microns, followed just seconds later. This tiny delay, mere moments in cosmic time, reveals something profound. It suggests that the energy of the flaring particles is changing rapidly. As the flare evolves, the particles lose energy, with the higher energy, shorter wavelength radiation fading first. The longer wavelength radiation, which needs less energy, lingers for just a little longer. This is exactly what scientists would expect if the particles were spiraling through magnetic field lines, cooling as they go. It's a microscopic flicker, with massive implications. But Webb's work is far from over. JWST and his team now plan to push the telescope even further to observe Sagittarius A continuously for 24 hours. An uninterrupted view like that would allow astronomers to minimize background noise and peer deeper into the flare patterns than ever before. You have to fight noise when you look at weak flaring episodes, JWST noted. But if we can monitor it for a full day, we should be able to see details that were completely hidden before. That's just incredible. And it's not just about one flare. It's about the rhythm, the frequency. Are these flare events random? Or is there a deeper pattern behind them? By capturing these flares across time, wavelength, and intensity, astronomers hope to build the first detailed map of how our galaxy's central black hole breathes, pulses, and changes. In the end, what we learn from Sagittarius A won't stay in the center of the Milky Way. It will ripple out, teaching us about black holes across the universe, the magnetic engines that drive them, and the raw power that shapes the galaxies we call home. Thanks for joining us on this journey across the cosmos. If you enjoyed exploring the universe with us, don't forget to like, subscribe, and hit the notification bell so you never miss a launch into the unknown.